this, I'll call it spiral review. It's kind of like an ACP problem here. It says, I'm going to do both these two in this one video here. The graph of y equals secant x is shown on the domain from 0 to 2.5 pi. Explain why the vertical asymptotes occur at 0.5 pi or half a pi, 1.5 pi, 3/2 pi, and 2.5 pi. Well, here's why. It's because if we know our rules about secant, secant is the reciprocal of cosine. So I'm trying to get my board working. Here we go. Secant is the reciprocal of cosine. So what that means for us, and this is on the formula chart, if you want to go Power School Learning, the formula chart is located there on the digital resources page, or if you're in Google Classroom, you go to classwork, formula chart appears there on the front page. And if I zoom in here, for reciprocal identity, secant is right there. It is 1 over cosine. Okay, so what that means for a vertical asymptote is the denominator equals 0. So the way you get a vertical asymptote again is the denominator equals 0. That's where the denominator equals 0. So in this case, we need to look, when does cosine x equal 0? And since cosine is x, if you think about it in terms of a unit circle, so here's your visual, it happens on the values where the x-axis is 0, so which would be on the unit circle. There it has an x value of 0, and down here has an x value of 0. If you think about it, this is starting at 0 radians. This would be pi over 2 radians, or 90 degrees, which is 0 radians, or I should, not 0, there we go, or 0 degrees. So it would happen at pi over 2, it would happen at 3 pi over 2. So remember, every time you add a pi, go in half a circle, so that'd be 3 pi over 2, this would be 5 pi over 2, 7 pi over 2, 9 pi over 2. It would just continue on that order. That's why it's because it's where cosine equals 0. You could also graphically see this by Desmos if you just typed in. So here's y equals secant x. There's that picture, and I'm going to change the axis in a second. And I'm also going to graph y equals cosine x. So you can see that the asymptote occurs every time we have a 0. And I want to change my domain to go, let me just do negative pi to 2.5 pi. Now I want to go past, I'm going to go to 3 pi. And I wish I could change how it's counting, but it's not so pleasant. So you can see that the asymptote here is occurring when that hits 0. So that's at x equals 1/2. A vertical asymptote, you can just type in x equals pi over 2. The reason I'm doing that is because that's that point. And you can see it separates this graph perfectly. I'll even do a dotted line, kind of like our graph over there. And if I copied this down, it would be 3 pi over 2, like what I was just saying. And then another one we would have, if I copied this, at 5 pi over 2. Notice everywhere that cosine is 0, you get that vertical asymptote between the graphs. And so now part 2 says, would the graph of y equals tangent x have the same vertical asymptotes as y equals secant x? Why or why not? And so if we look by visuals, y equals tangent x, and checked it, it does in fact have the same asymptotes. Now why? It's because tangent is equivalent to y equals tangent x is equivalent to sine x divided by cosine x. That right there is an identity we're going to learn about. Let me go back to the formula chart, which you will learn before too long, is called the quotient identity, which actually now I'm realizing the quotient identity is not on here. Okay, so never mind, it's not on the formula chart. So I gave you a sneak preview that we have reciprocal identities on there, but this is called the quotient identity. We'll learn this in chapter 5. That tangent, we say psi y cos x, tangent is y over x. I could have done it that way. That's y over x. Secant was h over x. Notice the x is on the denominator of both of these, so it'll have the same asymptotes because they both have cosine in the denominator. So same vertical asymptotes since tangent and secant have cosine in the denominator. That's your reasoning. Denominator. That's not how you spell it. Denom. Oh yeah, it was. Nator. Right there. There we go. So there's your answer to that one.